Hi, in today's video I would like to introduce you a very nice proof regarding Fourier series coefficient. Here is a following function. We have c of x equal to e0 divided by 2 plus the sum as n goes from 1 to infinity. E sub n is multiplied by cosine nx plus b sub n is multiplied by sine nx. Our goal, we are going to prove this e sub n as a Fourier coefficient equal to 2 divided by pi is multiplied by 0 as x goes from 0 to pi, c of x cosine nx dx. Okay, in fact this is the continuation of the previous proof. We already proved b sub n as a Fourier coefficient, but today I'm going to do the e sub n and e sub 0. Okay, so of course e sub 0 is related to e sub n. Since if you find e sub n, that means e sub 0 is easy to find. So now, before I proceed with the proof, I'm going to show the first identity as integral goes from 0 to pi. Cosine nx is multiplied by cosine kx dx equal to 0 if n different than k equal to pi over 2 if n equal to k. Okay, let's get started now by applying the trigonometry formula. So I have cosine of n plus k equal to cosine of n is multiplied by cosine k minus sine of n is multiplied by sine of k. Okay, for the cosine, n minus k equal to cosine n is multiplied by cosine k plus sine n is multiplied by sine k. Okay, so here is the first equation and the second equation. So now just I'm just going to add equation number 1 on equation number 2 to see what's given us. The last term will be cancelled out because we have sine n is multiplied by sine k. One is positive, the other one is negative. That means it will be 0. For the second one, cosine n cosine k, I have 2 times this one, so 2 times cosine n is multiplied by cosine k. This one will be 0 equal to this one, which is cosine n plus k plus cosine n minus k. If you take a look at this expression, we see only cosine is involved in this equation. This implies I'm going to apply x into cosine and integrate this one from 0 to pi. In order to evaluate the first integral, I'm going to put m as a substitution. Wherever the value of first integral will be the same as the second integral, because both functions are turning into the sine function, which is the same value. Okay, so now I will have 2 cases. If n different than k, so this integral as x goes from 0 to pi, cosine of m dx over m, I will have sine of mx over m as the bound goes from 0 to pi. So if you replace pi, if you replace x with pi, the sine of pi equal to 0 minus 0, because as you replace x with 0 will be 0 as well. So my integral here will be 0. So this one will be the same 0 because it's calculated in the same way. So this one will turn to sine, so the sine of pi will be 0. Okay, so that means the whole thing equal to 0. So this is equivalent as x goes from 0 to pi, cosine of nx is multiplied by cosine kx dx equal to 0 if n different than k. This is the first case. So I'm going to do the second case. If n equal to k, I will go back to the same expression. So I'm going to replace n with k. So for the first integral, it will be turned to 0, because I will have cosine to n x dx. The primitive of the cosine to n, it will be the same thing. I will cosine of 2n over 2n as x goes from 0 to pi, because we have the sine function. So the integral will be 0 as well. So I will have as cosine of 2n x dx by replacing k with n from 0 to pi equal to 0. But this one will be different, but the second integral will be different. As you're replacing n with k, that means the second integral as x goes from 0 to pi, cosine n minus n will be 0, x dx. As we know, cosine 0 equal to 1, that means our integral as x goes from 0 to pi, it will be dx, so it will be pi. Okay? Now, this is equivalent, the whole integral 2 is multiplied by, so the double integral as x goes from 0 to pi of cosine nx is multiplied by cosine kx dx equal to pi. Equivalent, the integral as x goes from 0 to pi, cosine nx is multiplied by cosine kx dx equal to pi over 2. Okay? This is for n equal to k. Okay. Now the first identity is proven. Now let's go ahead and prove this one. He said n as a Fourier coefficient. Let c of x be an even function such that we have c of minus x equal to c of x, because cx is an even function. And then we have the second condition. We have c of x plus 2 pi equal to c of x, because it's periodic function. So now let's set c of x equal to e sub 0. Let's choose c of x equal to e sub 0 plus e sub 1 cosine x plus e sub 2 cosine 2x, and so on and so forth until you get e sub k is multiplied by cosine kx, and so on. Okay, I'm going to apply cosine kx on both sides and integrate this expression as well in the same time. Okay, so I will write c of x. I'm going to leave this empty space equal to e sub 0 plus e sub 1 is multiplied by cosine x plus e sub 2 is multiplied by cosine 2x plus, and so on and so forth. I will have ak is multiplied by cosine kx. Okay, and so on. Multiply both sides by cosine kx. I will have cosine kx, cosine kx, and cosine kx. Cosine x will be at each term, cosine kx, and the last one cosine kx. Okay, in the same time I'm going to integrate this one as x goes from 0 to pi, dx. It will be the same thing for each term. Dx and the last one the same thing, as x goes from 0 to pi, this integral, the product of cosine kx and cosine kx. Okay, I'm going to highlight this one. If you take a look at each term, all terms are going to be 0 except the last term, which is highlighted with green. Okay, because as we mentioned in earlier proof, we proved cosine nx is multiplied by cosine kx equal to 0 if n different than k. Then if you take a look at each term, if you take a look at all terms, you will see k is different than n. For the first term, we have n equal to 1, and you have k, so that's mean 1 is different than k. So that's mean equal to 0. Okay. For the second term, it will be the same, 0. Same thing with the third one and fourth one, and all the way down until you get the last term. The last term, we know the last term of the series is always k equal to n. Since k equal to n, this one equal to pi over 2. That's what we have proved before. This term, for the first term, is different because we have cosine k. We don't have the product as we have before. Okay. So this one, so our integral as x goes from 0 to pi, c of x cosine kx dx equal to a0. I'm going to take a sub 0 outside of this integral because it's a constant. As x goes from 0 to pi, cosine kx dx. Okay. Now this one is going to be 0 as well, because when we integrate this one is given as sine of kx over k. Okay, as x goes from 0 to pi. If you replace x with pi, the sine of pi equal to 0. If you replace x with 0, it will be 0. So this integral will be 0. Okay, so this one is 0. This one is pi over 2. So that implies our integral as c of x, as integral goes from 0 to pi, is multiplied by cosine kx dx equal to pi over 2 of this integral, is multiplied by a sub k, because a sub k is a constant. I'm taking it out of this integral, is multiplied by the value of this integral, which is pi over 2. Okay, by replacing k with n and divide both sides by 2 over pi. So equivalent, I will have 2 over pi is multiplied by this integral as x goes from 0 to pi, c of x cosine nx dx equal to a sub n. Okay. In the same time, you can rewrite it as we know, since cosine nx is an even function, and we have chosen c of x is an even function as well. So the product of even functions is given as even function. That's mean the bound from 0 to pi equal to 1. That's mean the bound from minus pi to pi equal 2 times from 0 to pi. Okay, sub n equal to 2 over pi is multiplied by this integral as x goes from 0 to pi. C of x is multiplied by cosine nx dx equal to 1 over pi minus pi to pi c of x cosine nx dx. Okay, so now I have proven this one. I have done with this proof. If you have any question or suggest, just put it in the comment section below. Just consider the subscribe. Thank you for watching. I will see you in next video. Bye.